Thank you. So we know that in quantum Monte Carlo, twist averaging is very important to be able to achieve practical results for conducting systems. And yet it seems that we don't have a definitive standardized approach for how to occupy a given set of key points in these conductive systems. So here we propose a new grand canonical twist averaging scheme, which achieves charge neutrality by construction, and it also aims to reproduce the reference magnetization. Therefore, it actually avoids the large energy fluctuations, and it also avoids the post-processing needed to correct those energies. We will also show that it exhibits the most robust convergence of total energy and magnetism to the thermodynamic limit when we compared it against 4 other twist averaging schemes. We will show applications on non-magnetic FCC aluminum and ferromagnetic BCC iron. And overall, what we see is a smooth convergence of total kinetic potential energies, as well as other observables such as cell magnetization, atomic moments, and charge densities. So as a reminder, under twisted boundary conditions, your many-body wave function will pick up a phase when you have a translation of single electron by a lattice parameter. And then you can evaluate any observable by averaging over those different twisted boundary conditions. Now, when it comes to the question of how to occupy those key points, there are a few ways to go about this. Perhaps the most popular way is the so-called canonical twist averaging using the lowest DFT eigenvalues. This is what we call here as CTA DFT. In this case, you have each twist to be charge neutral, but it may exhibit a fluctuating moment for each K point. Another one is the canonical twist averaging used in insulators. Again, here you have charge neutrality for each K point, but it will also not exhibit any fluctuating moment. So the moment will be also fixed for each K point. However, the problem with these CTA schemes is that they fail to accurately represent the discontinuity of occupations at the Fermi level. And to address that, grand canonical twist averaging was introduced some time ago. Here we call it GCTA DFT. This is the conventional GCTA that will occupy the single particle levels strictly based on the Fermi level, where the Fermi level is occupied, the Fermi level is obtained at the thermodynamic limit. So in practice, it would be a very dense DFT K-mesh where the Fermi level is coming from, as you can see here. However, the problem with this one is that if you do a twist averaging for any twist, you may end up with a charge in your system. And so what that means is that you will see a wide fluctuation in your total energy and also your charge densities. And so here are the new GCTA methods that we propose. We propose 2. The one on the left is we call GCTA AFL, stands for GCTA with adapted Fermi level. So in this scheme, it is very similar to the conventional GCTA, but now we have shifted the Fermi level such that once you do the twist averaging, you get a charge neutral system for any value of Z theta, where the Z theta is the number of twists in your supercell. And to find that adapted Fermi level, all you have to do is you consider your supercell, which is characterized by Z theta, number of twists, and ZT, which is the number of primitive cell in your supercell. And then you combine all the Poncham eigenvalues to a list, and then you sort them. Here in this case, you have up and down spin channels in this list. And then just from electron counting, you can come up with an index. And then using that index, you can set the adapted Fermi level. So what this results in is a charge neutrality for any number of ZT and Z theta. And also here, the Fermi level is set locally for up and down spin channels. But that can introduce some deviation to your reference magnetization if you have magnetization in your DFT. So to fix that, a yet even more improved scheme is the GCTA SAFL. This is the GCTA with spin adapted Fermi level. This is similar to the previous one, but now you shift the Fermi levels for up and down spin channels independently to be able to better target the reference magnetization. So again, what you do is you sort all of your eigenvalues for up and down separately. And then again, you can come up with these indices, which again comes from electron counting. And then in this case, you have the reference magnetization in your recipe. And then using those up and down up and down indices, you can set the Fermi levels for each channel independently. This one again results in overall twist average system being charge neutral, but it will also closely follow the reference magnetization. Let me jump to the results. I will start with the aluminum at the smallest conventional cell, so 4 atoms. So on the left, what I'm showing is the number of electrons per atom as you increase the twist mesh size in your QMC calculation. If you look at the gray dotted line, that's the conventional GCTA. The number of electrons will fluctuate as you increase the twist mesh size. However, if you go to very, very dense K points, you will see that it will eventually go to the correct number of electrons. The canonical one, red, which you can't really see, but it's behind the green one. That one and the new green one, they have the correct number of electrons from the outset. So for any number of twists, you have the correct number of electrons. And the way it is achieved, as I said, instead of fluctuating the number of electrons, you fluctuate the Fermi level as you change your twist mesh size. And if you look at the inset, this is the Fermi level, by the way, as you increase the twist mesh size. If you look at the inset, the Fermi level will eventually go to the GCTA Fermi level, which is shown by the flat gray line here. And in that case, it is held constant. So, okay, how do the results look? Again, I'm continuing on with the 4-atom cell of aluminum. On the left, you see the DMC total energy per atom as you increase the twist mesh size. So again, the conventional GCTA shows a wide fluctuation because there's a charge. CTA and the new GCTA actually converge very fast. However, if you notice that the GCTA has a much lower energy for this given small cell, this is actually considerably lower energy if you look at the energy scale. And also, if you look at the energy components, such as kinetic energy, you will see a similarly robust convergence of the components. And on the right, this is the total energy variance. In this case, the CTA total energy variance is actually smaller than the GCTA methods. And this is actually expected because now you have charges for your K-point twists. And this is the price that you have to pay to get the lower total energies. Okay, now let me show similar results for BCC iron. Again, this is a small cell with 2 atoms. On the left, you see the Fermi level. Again, the conventional GCTA is flat with gray. The GCTA AFL, the yellow one, is shown here. And then the purple and the green ones, they are the up and down Fermi levels for the GCTA S AFL. And you see that as you increase your twist mesh size, they all go towards the conventional GCTA DFT value, which is expected. And then if you look at the DMC total energy, again, you see this wild fluctuations for conventional GCTA. You have other CTA methods, and then the new GCTA methods, they converge fast, and then they again have lower energies than the canonical twist averaging. And again, if you look at the energy components, such as kinetic energy, you see similarly robust convergence of the components as well. Again, continuing on with the smallest BCC cell of iron, 2 atoms. But now I'm going to show what happens to the magnetization because this is a ferromagnetic system. On the left, you see the cell magnetization per atom as you increase the twist mesh size. Here, the reference value, which is obtained in DFT, is shown with this purple line. And here, you see that the new green one converges very fast, whereas others, you need to go to very large dense K meshes. For example, if you look at the inset, the GCTA AFL will also converge to the correct magnetization, but at very large K points. In this case, actually, GCTA DFT, the conventional one, actually also gets the correct magnetization, surprisingly, even though the charge may not be correct. And then if you look at the DMC moments, which is coming from the spin density around the atoms, you will see that it actually mirrors what is shown on the left very, very closely. And that tells you that it's very important to set the correct occupations for each K point to be able to achieve fast convergence in the magnetic moment as well. Okay, so now what happens if you do supercells and then try to extrapolate to the thermodynamic limit? I'm coming back again to aluminum. On the left, you see DMC total energy as you increase the supercell size, where I have the conventional cell 1 by 1 by 1, 2 by 2 by 2, and 3 by 3 by 3 here. If you look at GCTA DFT, it's actually a nice line. However, it actually goes to the incorrect thermodynamic limit value because there's a charge. CTA and the new GCTA go to roughly the same value, but if you look at the red curve, there's a big change of slope as you go from like small cell to the larger cells. Whereas with the new GCTA, it's a very nice line, and even with the smallest cell, you have a consistent slope as with the larger supercells. And also, if you look at again the energy components such as the kinetic energy, it's not as perfect as the total energy, but again, if you have a much nicer linear extrapolation with the GCTA method. In this case, we wanted to check if this thermodynamic limit value of total energy is correct. And so to do that, we compared the cohesive energy with experiments. You see our value here in the experiment, and we were surprised that the agreement is very good. Actually, here it's only off by 6 millieV. And we estimated that the systematic error in this case is actually better than the chemical accuracy. Again, coming back to iron, extrapolating to the thermodynamic limit, you see in total energies very nicely linear extrapolations. Some of the CTAs again show some change, but in this case, total energies, it's difficult to change the difference, see the differences. But if we look at the energy components, you can see better the differences. For example, with this red line, you see a big change in the slope, whereas with the green and the yellow one, it's not perfect, but it's a move in the right direction. So we think this new GCTA methods could improve lots of our scientific applications. For example, metal insulator transitions, equation of state for lattice parameters as you compress or stretch. It would also improve the Fermi surfaces. And I want to note that here I have employed a uniform grid, but this GCTA actually doesn't care about this. You could use any type of K grid. It could be a pseudo-random or quasi-random K points. However, the GCTA SAFL works only in collinear systems. If you want to do a non-collinear, you can use GCTA AFL, and that should work because it only looks at the lowest eigenvalues. We plan to implement both of those on Nexus in the future, so you will be able to just pass GCTA SAFL or GCTA AFL, and then it would populate the correct up and down occupations, as you can see here in the QMCPACK input for each twist. For now, it's user's responsibility to set this correctly. So in conclusion, we have proposed a new grand canonical twist averaging scheme, which is an improvement over the conventional one. Overall, the GCTA SAFL shows the best convergence to the thermodynamic limit in the context of total energies and magnetism. It also shows a rapid convergence of energy components and magnetic moments as the number of twists is increased for a given simulation cell. Both of these methods result in lower total energies than canonical ones for a large number of twists, and they also exhibit a robust supercell extrapolations, potentially allowing only the use of the smallest cells. Also, the advantage here is that the change is very simple, and it only requires the availability of single particle orbital eigenvalues for each twist, and then some light pre-processing before you submit the QMC job. And also another advantage is that these schemes do not require any post-processing corrections, and that's what I showed. I have shown only the raw quantities in this presentation. I want to thank Ganesh and Jaren. They were key in developing the ideas behind these schemes, and also I want to thank you for listening, and I'll take any questions.
Thanks very much, Gani. Very interesting talk. Unique. Open for questions. Anyone online is welcome to ask a question. So, of course, I have a question. You spoke about, this is a question about properties other than the energy. So you spoke about moments, and I was wondering if you have studied other observables or even just the charge density in more generally to see how they converge in this new scheme.
Yes, so we see good convergence in the charge densities as well. Let me see if I have that. Oh yeah, I do have it. So I didn't show it because I didn't have time, but this is the charge densities. So in this case, this is when you increase the supercell, but I also have it when you have a small supercell, and then when you increase the number of twists, there's a good convergence in GCTA. In that case, the CTA and GCTA are close together, but there's still some improvement. However, if you look here, the conventional GCTA is actually quite off, and you can't even see in the scale because the charge, the charge is basically way off. If you look at the energy scale, this is quite small. And so that's the difference between these schemes, and charge density seems to be a bit more robust quantity than the magnetic moments. But the focus has been being able to converge the magnetic moments, because we were studying BCC iron, and it seemed that the phase of the BCC iron seemed to be a key in getting a different flow of energy, and that actually what spanned this work. So the magnetic moments were the key, but yes, we have looked at other observers such as the charge density and the Fermi length, etc. And so overall, all of the observables that you can get with CTA seems to be okay with this new GCTA, and that's what we have seen, because they have charge neutrality, you don't need any post-processing, and everything seems to be coming out very well aligned so far that we have seen.
Thank you. Any questions? Is that a question at the back, or are you
Oh, no,
stretching?
I'm just stretching.
Okay.
It was a great talk.